Suppose that a mass weighing 10 pounds stretches a spring 2 inches. If the mass is displayed an additional 4 inches and is then set in motion with an initial upward velocity of 0.2 feet per second, determine the position of the mass at any later time. Also determine the natural frequency, period, amplitude, and the phase of the motion. In any case, let's try to find what is given. Mass weighing 10 pounds. So the mass is 10 pounds divided by 32 feet per second square. Okay, then that is 5/16. This mass stretches a spring 2 inches. Stretched length. That means when we divide this weight divided by stretched length, 10 divided by 2 inches, which is 2/12 feet, that gives a spring constant K. 10, that's the weight, over stretched length, that comes out to be 60. If the mass is displayed an additional 4 inches and is then set in motion with an initial upward velocity, so this is initial displacement, so u0 is 4 inches, that means 4 divided by 12 feet, so 1/3 feet. Initial upward velocity, so the velocity u prime 0 is 0.2, upward means it's negative. Okay, and we need to find the position of the mass at any later time, so ut equals what? So here is the motion, here is the differential equation that models this mass spring problem. M u double prime plus gamma u prime plus ku equals 0. In this question there is no mention of gamma. Okay, there is no mention of, so we have no viscosity, so gamma is 0. So m u double prime, m is 5/16 u double prime plus k is 60 u equals 0. Now let's multiply, divide by 5/16, which is multiply by 16/5. Then we get u double prime plus 60 times 16/5. That will be 5 goes 12, 12 times 16, 192 u equals 0. Now we want to solve this differential equation along with these two initial conditions. So basically we are solving an initial value problem. So we find characteristic equation, which is r squared plus 192 equals 0. So r equals, move this over, take square root of negative 192. So r equals plus minus, this is 64 times 3, 64, so 8 square root of 3i. So we have complex conjugate roots. Then the solution ut is c1 cosine 8√3 t plus c2 sine 8√3 t. And to use this second initial condition u prime, we need to find the derivative. So derivative of cosine is negative sine, so negative 8 constant outside sine 8√3 t plus derivative of sine is cosine, so 8√3 c2 cosine 8√3 t. Okay, now let's use the first initial condition here. So using u at 0 equals 1/3, we get u0 1/3 equals c1 times cosine 0. Cosine 0 is 1, so c1 plus c2 times sine 0, which is 0. That is same as c1 equals 1/3. And using the second initial condition here, so u prime 0 equals negative 0.2. So we get negative 0.2 equals sine 0, that will be 0, so we don't have to write anything here. This is 0 plus 8√3 c2 cosine 0, which is 1, don't have to write, or c2 equals negative 0.2 divided by 8√3. Okay, we can simplify this. This is same as negative decimal 2. If we remove the decimal, it becomes 80. 2 goes 40 times, so it is negative 1/40√3. Okay, thus the motion of the spring at any time ut. So we go back here, that's the solution, and we just found C1 and C2 using the initial conditions. Thus the motion ut is C1, that's 1/3 cosine 8√3t plus C2, which is negative. Okay, so minus 1/40√3 C2 sine 8√3t. Okay, now we need to answer other questions as well. So we just found the position of the mass at any later time. Okay, that's it. Now we need to find the natural frequency. Natural means there is no outside force. Okay, that's why natural frequency, period, amplitude, and phase of the motion. So let's first find the frequency. Then the natural frequency, or just the frequency, omega naught natural. That's already found here. This whatever we have inside 8√3, this is it. Okay, so the formula is always k over m, square root of k over m. Okay, that's the natural frequency. So we found here, so 8√3, which is in fact, if you want to find the decimal, 13.86 or 13.856. It's the radian per second. As soon as we have the frequency, then we can find the period. Okay, that's 2 pi over omega naught. 2 pi divided by omega naught, we get, use your calculator, 0. This is approximately equal to 0.45345. Okay, seconds. Next we need to find the amplitude. That's the r, that is given by square root of c1 squared plus c2 squared, which is square root of c1, 1/3 squared, 1/9, plus c2 squared, here is c2 squared, so 1/40 squared, 1600 times 3, so 4800. Now you use your calculator, whatever you get, that many feet. And finally the phase is given by tangent inverse of c2 over c1 plus pi. Okay, could be plus pi, we'll determine in a moment. That's tangent inverse of c2, that's negative 1/40√3 divided by c1. c1 is 1/3. Look at c2 means sine. Sine is negative, cosine is positive. So we are in fourth quadrant because cosine is positive here and sine is negative. All students take calculus. So cosine is positive, sine is negative. Sine is negative, and tangent inverse gives us value. It's a negative value on the fourth quadrant, positive value on the first quadrant. So we'll be good. We don't have to use plus pi. This is it. Use your calculator. Okay, make sure the mode is in radians. We get negative 0.4327. Okay, radians final. Okay, use your calculator and find this small number.